Five levels of chain rule in calculus. So basically, in calculus, like there's in derivative, you will need chain rule if like the functions are composite, right? And yeah, like those really simplify our tasks. Instead of evaluating the composite functions, we can just use chain rule, and that does a lot of simplification. And yeah, even in multivariate calculus, you will learn a few more generalized versions. And yeah, definitely, if you are going to take calculus, you will need these things. And so yeah, if you are like taking it in the future, I think if I summarize this by giving some intuitions and like helping you understand, this will be helpful. So I think yeah, you can watch this video. And yeah, for all of these rules, I will try to give you like the intuitions and understandings of how even you can derive these formulas even though you forget it all, right? So I think that can help you to like rebuild the formulas later on by yourself. Okay, let's start now. First of all, single variable chain rule. Single variable chain rule. Now let's say we have y as a function of x, and again x as a function of u, right? Now, and if we want to differentiate y with respect to u, right, in this case one of the ways would be to first of all find the function f of g of u, right, because x is g of u. So you can find this net composite function f of g in terms of u, and then you can differentiate it with respect to u, right? But there's also a chain rule. Like what it says is I can introduce a dx over here in denominator and dx over here in numerator. Yeah, now this is not the formal proof, but you can say look it like the dx being cancelled, so eventually they give dy by du, right? So that gives us the intuition like how we can like how we can like just understand yeah, this is working. Yeah, we get that intuition anyway. Now the benefit of like making this formula dy by dx times dx by du is that now since y is a function of x, we will be able to differentiate this, right? And also we will be able to differentiate the other formula, which is x is just g of u, right? So now it's a lot simpler. We don't need to find this function. We just got the answer easily. So that's the benefit of having this chain rule in your pocket. Now let's go to the next formula, which is multivariable single parameter chain rule. Multivariable single parameter chain rule. Now also like let me tell you that this single variable chain rule can be generalized to a few more like compositions as well. Let's say if I had y is equals to f of x is equals to g of u is equals to s of t, right? And so eventually y is f of g of s of t, right? So even in this case you could have found out dy by dt directly by using dy by dx times dx by du times du by dt, because eventually it looks like du cancel, dx cancel, dy by dt, right? And so like this formula d by dx of f of x, d by du of g of u, d by dt of s of t can help you compute the derivative faster. Okay, now let's go with this one, multivariable single parameter chain rule. Now let's say we have a function g which is a function of x and y, right? And again these x and y are based on like t. Let's say this x and y are functions of t, g1 of t and g2 of t, right? Now in this case like now if I want to differentiate let's say g with respect to t, now in this case we will need the multivariable single parameter chain rule, and let me try to introduce this in a more intuitive way. So now first of all, let's say if you want to find the change in g, if you want to find a small change in g, that will be sum of the change in g caused by change in x plus change in g caused by change in y, right? Yeah. So now the change in d will be caused by both x and y. And again, this x and y, the change in those will again be caused by t, right? So now how you can see this is the dg, you can see it as okay, so g is a function of g is basically the function of x and y, right? So how you can see this is change in the function caused by x plus change in the function caused by y. Now how you like see this is just the rate of change of function with respect to x times the change in x, which gives the total change in the function due to x. Over here, this is the rate of change of the function with respect to y times change of y, which gives us the change in the function caused by y. Now if we sum them up, we'll get the total change in d, total change in g, right? So this is where like our formula comes from. Now you can just like see it like we introduce dt over here, like we divide all the terms by dt, right? Now the notation, you might have noticed that there are partial derivatives and total derivatives, because this x, y are just functions of t, so we are taking total derivative, right? But these f's, these are the functions of x and y, like they have x and y in them, so if you just want to differentiate with respect to x, we need to have partial derivatives. So that's the reason. Now this is what the multivariable single parameter chain rule looks like, right? Even if let's say like z was a function of x, y and w, and all of them were simply the functions of t, even in that case this would hold true. Our like chain rule would just be dg by dt would be equals to partial derivative with respect to x by dx times dx by dt plus partial f by partial y times dy by dt plus partial f by partial g times dg by dt. So you can generalize this for like how many variables you might have, right? So this is our multivariable. There are multiple variables in here, but eventually they all like come from the same parameter t. So this is our multivariable single parameter chain rule. Now next one is multivariable multi-parameter chain rule. Now what that means is multivariable multi-parameter chain rule. Now for this one, how we can look at this is, now let's say if I have g as function of let's say x and y, right? Again, if x is a function of s and t, and y is also a function of s and t, so here there are multiple variables, and again those variables like come from multiple parameters, right? So in this case, like how will we deal with, like we will like try to deal with the change in g caused by this s and t individual wise. So basically the partial change in g we are trying to find change caused by s, so that will just be like df by dx, so partial f by partial x times like the partial x, right? Now let's say we want the rate of change caused by s, then we can just introduce a partial s, like it's the same thing, but like just like in the single parameter one. But right now, since there are two different variables, we are like writing over here partial, because it's not the entire rate of change, because there are two variables, right? So over here also it's partial, because the change in x is caused by two variables, s and t, but we are just looking for the s right now. So the partial, like the rate of partial change of x by partial s will be equals to partial f by partial x times partial x by partial s plus the same thing, right? It's almost the same formula, but since this like there are other variables that g accounts for s and t, so that's why we have the partial sign. Everything else is almost the same. Yeah. Now similarly, partial g by partial t will be partial f by partial x times partial x by partial t plus partial f by partial y times partial y by partial t. So yeah, these are the like multi-variable, multi-parameter chain rules, and you can generalize it in the same way I told earlier, right? Even if there are multiple parameters, we will have like multiple of these partial functions. Yeah, if you had, let's say, even another u, so you will just find partial g by partial u in the same way, and I think that makes sense, right? Okay, now let's go to another form thing, which is multi-variable single parameter higher order chain rule. Now we need to do some maths for this one. Like till now it was just based on intuitions. Now we need to do some maths. Multi-variable, multi-parameter higher order chain rules. Okay, now till now like the order was just one, right? Till now the functions were just the first order derivatives. Now we are going to higher order derivatives. But before that, let me like say you something interesting about from. Let me say you some interesting result that we can get from this one. So let's say we have g as f function of x and y, right? Now let's say y was also a function of x, and x is axis itself, right? So if this was the case, now if I wanted to find, let's say, dg by dx, this should just be partial f by partial x times dx by dx plus partial f by partial y times dy by dx, right? Now this should just be dg by dx is equals to, this should just be 1, right? You can see it as like a division, and so we'll just have partial f by partial x plus partial f by partial y times dy by dx. So this is a like slight modified formula with the same rule. So if you want to like differentiate z with respect to x, if like y is a function of x, then yeah, you can use this formula too. Now let's go to this one. We want to find, let's say, like for now, let's say the higher order just means second order derivative. You want to find the second order chain rule. Now how will you do that? Okay, now for that, let us for now. Wait, first of all, let us deal with multi-variable single parameter higher order chain rule. Then we will go to multi-parameter. Okay, multi-variable single parameter. Okay. Now let's say if you have g is equals to f of x comma y, right? And both x is a function of t and y is also a function of t. So in this case, we want to find out like d square g by dt square. How will we find this? Now there's a fair bit of maths involved, and get ready to do that maths. In fact, this is the only maths involved in this video. Like all other ways were just intuitions. Okay, now let's show this. Now first of all, we know that like dz by dt was partial f by partial x times dx by dt plus partial f by partial y times dy by dt, right? Okay, now let's say we want to again differentiate this with respect to t. Yeah, so we differentiate both sides. Right? Again, we differentiate, we use the additive property of derivative. Okay. Yeah. Now this will be, notice that here's the product, right? So we'll just use the product rule first. So then we will have d by dt times df by dx, the derivative of first times the second as it is, plus the first as it is and derivative of second. And notice that this was not a partial, actually this was a total derivative. Okay, I'm sorry for that. Okay, and then okay, this was partial actually. Okay, d by dt of dx by dt, right? This is just the product rule. Over here also we will have the product rule. We will have d by dt of df by dy, partial f by partial y, and then dy by dt as it is, plus partial f by partial y times d by dt of dy by dt, right? Okay, now after this, notice that like these things are, we can write it easily as d square x by dt square, right? Just second derivative of x with respect to t. We can also write easily at this is second derivative of y with respect to t, right? Now over here, like notice that partial f by partial x will again be a function of x and y, right? This partial f by partial x again some function of x and y, right? So to differentiate this with respect to t again, we need to use the same multivariable chain rule that we used earlier. So this will be first of all, I'm sorry. Okay, so first of all, this will be partial with respect to x times dx by dt, and with respect to y times dy by dt. I guess you remember this, right? And this is multiplied by partial x by partial t. Looks good? Looks good, right? Is there any error? No. Okay, and yeah, there is error. I think there's error. This should be dx by dt, right? So this is dx by dt. My lord, this I'm missing a lot. Looks good now? Yeah, now it looks good. I'm sorry for that. Okay, now dx by dt plus this is partial f by partial x times d square x by dt square, plus this is now again, this is again a function of x and y, so we'll use the same multivariable like chain rule. So this will be partial with respect to x times dx by dt plus partial with respect to y times dy by dt, right? And at last we also have partial with respect to y times d square y by dt square. Okay, now this will be okay, now this will be partial square f by partial x square times dx by dt plus partial square f by partial x. Okay, order won't matter due to the Clairaut's theorem, but again, let me still maintain the order. Partial y partial x times dy by dt dx by dt plus this is partial f by partial x d square x by dt square plus this is, hey, isn't here anything to multiply? Oh, there is. There is, right? Yeah, there again, there is this dy by dt. Why did I forget that? There is this dy by dt. I'm actually like messing this up, and I just hit that. Okay, so over here we also have dy by dt, and then this is partial f by partial y times d square y by dt square. Okay, good. Now this is partial square f by partial x partial y times dx by dt plus partial square f by partial y square dy by dt plus partial f by partial y d square y by dt square. So finally we are having partial square f by partial x square, now dx by dt whole square. Now I would like to write this together with the this one over here. partial square f by partial y square, we will have dy by dt whole square, right? Now we know that partial square f by dy dx, this is same as this thing, because this from the Clairaut's theorem that the order won't matter in the like partial derivative x y or y x, that's they are same. So we have, and also like dy by dt multiplied with dx by dt as well as over here dx by dt with dy by dt, so they are same. So I can write this as 2 times partial square f by partial x partial y times dy by dt dx by dt, right? They are basically same. Now these two terms are remaining, yeah, and they will be partial f by partial x d square x by dt square plus partial f by partial y d square y by dt square. And this is it. This was a lot long. So this is our d square z by dt square, right? This is our d square z by dt square, d square z by dt square, d square z by dt square. So we'll basically have the partial square f by partial x square times the counterpart. It has the counterpart, it has the counterpart, maybe they have the counterpart too, and yeah, and then partial f by partial x times d square by dt square. Now you can just remember this if you want to. Now yeah, this is the multivariable single parameter chain rule, higher order chain rule. Now the last one is not so different. Last one is just like how the second one generalized the third one. Similarly the fourth one will generalize the fifth one. So in the multivariable multi-parameter higher order chain rule, the multivariable multi-parameter higher order chain rule. Okay, now for this one, let's say z is a function of x and y. Again, x is a function of s and t, right? S and t, and y is a function of s and t. Now if we are considering like the partial square z with respect to s, since like in that case t will just be constant, it won't really matter. Like you can just go on with the same thing. Now this will just be over here, instead of dx by dt, they're only partial though, to make sure that you make that correction. So this will just be d square f by dx square times dx by dt, or sorry, partial x partial whole square. It's the same formula in different way. Now partial f by sorry, it's not a t, we are doing with respect to x right now, I'm sorry. Okay, and then dy square, dy partial y partial partial square f by partial y square, partial y by partial s square, plus 2 times partial square f by partial x partial y times partial x by partial s, partial y by partial s, right? After that, plus partial f by partial x times partial square x by partial s square, plus partial f by partial y times partial square y by partial s square. So this is it. Now similarly, for with respect to t, this will just be partial square f by partial x square times partial x by partial t whole square, plus partial square f by partial y square times partial y by partial t square, plus 2 times partial square f partial x partial y times partial x by partial t, partial y by partial t, plus partial f by partial x times partial square x by partial t square, plus partial f by partial y times partial square y by partial t square. This is the ultimate level of general. Okay, guys, I don't know how good of a job did I do while explaining these, right? Uh, you can get this intuition also from the multivariable playlist in the Khan Academy, which was done by the Grant Sanderson. So yeah, I think you did get us some idea, right? Hope it was helpful. The single variable chain rule, multi-variable chain rule, multi-variable multi-parameter chain rule. Oh, I forgot the and then multi-variable single parameter higher order and multi-variable multi-parameter higher order chain rule. Hope it was definitely helpful. And yeah, thanks for watching, and I look forward to seeing you in upcoming videos too, and I do hope that these contents are helpful for you guys.